Hello, students. Module 9, Lesson 1, One-Way Analysis of Variance. Before we get into the ANOVA, let me recall something from Module 7, Lesson 3. So, suppose we have this random sample of size n from a normal distribution, mean mu x, standard deviation sigma. And then we have another random sample, size m, from a normal distribution, mean mu y, standard deviation sigma. Okay, so we can test if the means are the same, where our null hypothesis is that mu x equals mu y, and our alternative would be mu x is not equal to mu y. We used a two-sample t-test with equal variances. Here, this part was important, that they came from normal distributions with the same standard deviation, or equivalently, the same variance. Fantastic. Well, let's suppose we have more than two populations. We can use the ANOVA, it stands for Analysis of Variance, to test for differences in the population means. Okay, here's the setup. So instead of having two random samples, we have G random samples. For this beginning discussion, I'm just going to assume that all my random samples have the same size, although I'll make a comment later that we don't need that assumption. So we have random sample 1 is of size n, normal distribution, mean mu1, standard deviation sigma. Random sample 2 is of size n, here it's little n, normal distribution, mean mu2, standard deviation sigma, all the way out to random sample G, size n, from a normal distribution, mean mu G, and standard deviation sigma. Just like with the two-sample t-test with equal variance in the ANOVA, we are assuming we have the same variance for all of the G groups. I make this remark, what you will see in our textbook and many textbooks, we generally use lowercase letters to denote the actual observations, and I have the corresponding lowercase letters here. Okay, so our null hypothesis is that all G means are the same. The alternative, at least two means are different. Okay, to test this, H0, we will separate the variation in the data into two components. We will have between group variation and within group variation. Just to illustrate this, let's look at this very small artificial data set. So I have these three data points, 2, 3, 1 are in the first group. These three data points, 3, 2, 4, maybe I should highlight my groups. This is the first group, this is the second group, and this one is the third group. So these three data points, 2, 0, 1 in the third group. All right, what's the idea behind this between group variation and within group variation? Well, if we just look at group 1, this would be within group variation. Now I can just copy and paste. Similarly, if we look at just group 2, here's our within group variation. And then if we look at group 3, maybe I should put it on this side. Here is our within group variation. What would be the between group variation? Well, if you look at group 1, the sample mean is 2. So I can plot this over here. If you look at group 2, the sample mean is 3. And if you look at group 3, the sample mean is 1. So this would be the between group variation. The variation among the group means gives us between group variation. So Now that we have an idea from this picture, let's get into the mathematics. The variation in the data is summarized by the sum of squares of the deviations from the mean. We let y bar be, well, in words, the overall mean of the data. Here, this capital N is little n times little g. So I have g groups, and each group has n observations. Then we have this y sub j bar. Here, you can see this is the jth group mean. Next, we have a definition of these three measures of variation in the data. First of all, we have sum of squares total. This measures total variation. We subtract Yij from the overall mean, square, and then we add up over all possible observations. We have sum of squares within. This measures within group variation. We look at the difference from some observation Yij to the group mean, and we square, okay, and we add up overall observations in our data, and then we have the sum of squares between. This measures between group variation. We take the group mean minus the overall mean squared, and then we add up overall observations. Let's see, let me make a remark here. You notice on this sum, we sum I equals 1 to n, but this term has no I in it. So you could factor this out of the first sum, I equals 1 to n, and you will just get a sum j equals 1 to g of n times this difference. The jth group mean minus the overall mean squared. Similarly, you could factor out the n in front of the sum. I think in a few pages, I'll mention a different way to think about sum of squares within, but for now, we can move on. And I want to talk about an important equality of ANOVA. It is the following. The sum of squares total equals the sum of squares within plus sum of squares between. What this is saying is the total variation is partitioned into the within groups variation and between groups variation. Okay, so we can justify this equality with some algebra. Let's go back and copy some of these formulas. All right, well, let us start with right here. You notice all three sums are summing over all observations, all capital N, which is n times g observations. So I'm just going to start with this term, Yij minus the overall mean squared. Well, we can do a little trick here where we subtract off the group mean and also add it back. You notice I am not changing the equality here. Okay, now I want to think about this here and here. So we can do this, Yij minus the group mean squared. That's the first. Then the last would be plus the group mean minus the overall mean squared. But then I have this inner and outer. So I'm thinking about first, outer, inner, last here. My inner and outer, we get the following: plus 2. We have Yij minus the group mean and then times the jth group mean minus the overall mean. Okay, well, now what we're going to do is add all of this up, 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 overall I and j. You notice when I do that, this part gives me, aha, sum of squares within. And this part gives me, aha, sum of squares between. But the question is, what about this? So what I need here is if I add j equals 1 to g, and then I equals 1 to n of this, we get 0. I have just rearranged things, but what we need is the sum here to be 0. And then we will have justified that the sum of squares total equals the sum of squares within plus sum of squares between. Okay. The first thing that we can do is we observe right here that there is no I in this term, and so we can factor this outside of the first sum. Let's do that now. Oh, this is looking really nice because what happens when we add from I equals 1 to n of y I j? Well, we're going to get n times the group mean. And similarly, if you add from I equals 1 to n of the group mean, well, there's no I in it. So we just get n times the group mean. And so now if you stare at this part is 0. So maybe I should outline this. So the overall sum is 0. Fantastic. Well, if you look at our work, we see so many indices, so many overlines, I's and J's. However, I think as we talked through it, it wasn't too bad. We used algebra to justify that the sum of squares total equals sum of squares within plus sum of squares between. Okay, I want to mention an equivalent representation of this model. So we can have this random sample from a normal distribution, mean mu j, standard deviation sigma. This is equivalent to saying that this ij term equals the mean plus some epsilon ij, where epsilon ij comes from the normal distribution with 0 mean, standard deviation sigma. Here, this epsilon ij is random noise. This is the way to think about this. So the within group variation, this sum of squares within, depends only on the epsilon ij's because this is the same throughout the group. For the between group variation, it's a little bit different. If you're considering H0, so under H0, where all the means are the same, mu1, mu2, mu3, out to mu g, then the sum of squares between also only depends on the noise, epsilon ij. However, under the alternative hypothesis, let me go back to the first page, where at least 2 of the means are different, then the sum of squares between, or between group variation, depends on the noise, the epsilon ij's, as well as the mu sub j's, the means. Okay, so we reject H0 if the sum of squares between is greater than we expect from pure noise. This is the idea here, and then we will get into some statistics on the next page. We should reject H0 if this ratio, sum of squares between, divided by sum of squares within, is too big. Okay, well, we need distributions of these two under H0 in order to have a statistical test. So before I get into those, let me remind you something from Module 6, Lesson 2. This is when we had sampling distributions. If we have a random sample from a normal distribution, mean mu, standard deviation sigma, this sample variance, which is defined this way, 1 over n minus 1 times the sum, where we take xk minus the sample mean squared and add that up. Well, we have n minus 1 s squared over sigma squared is distributed as a chi-square random variable with n minus 1 degrees of freedom. Now, as a remark, you see you could also write this as follows, that n minus 1 s squared is distributed as sigma squared times this chi-square with n minus 1 degrees of freedom. Now, given that recollection, it should not be surprising that we're seeing this chi-square over here for the distributions of sum of squares between and sum of squares within. In particular, I can talk a little bit more about this one. So stare right here and compare it to right here. You see we have Yij minus the group mean squared, and then we're adding up over the n observations, the random sample of size n. Well, you see that is also here. So this part, we can rewrite this sum of squares within as a sum, j equals 1 to g. We have, this is n minus 1 times, I'll write it as say s sub j squared, where I'm thinking about sj squared as the sample variance in group J. What we see is for each j, we have sigma squared times a chi-square random variable with n minus 1 degrees of freedom. Then you add all of those random variables, it's another sigma squared times a chi-square random variable, and the degrees of freedom add. Here, recall that capital N is little n times g. So this at least gives you some idea about the second one. And similarly, sum of squares between, we have this sigma squared times a chi-square random variable with g minus 1 degrees of freedom. Next, I need to define the mean squares. Generally, you take sum of squares divided by the degrees of freedom. That's what you notice here for mean square between, sum of squares between, divided by its degrees of freedom. This is true for mean square within, sum of squares within, divided by its degrees of freedom. So in words, we are dividing by the degrees of freedom, which is the expected value of a chi-square random variable. So in a sense, we are normalizing this quantity by its degrees of freedom. And similarly, we are normalizing the sum of squares within by its degrees of freedom. This gives better quantities to compare. So here we go, our theorem under the null hypothesis, which is that all of the means are equal. This ratio, we take mean square between divided by mean square within. It follows an F distribution with g minus 1 and n minus g degrees of freedom. Capital N is n times g. So some notes. Under H0, the observed ratio should be around 1. An alpha level test would reject H0 provided your observed statistic is bigger than this F sub 1 minus alpha. This is the 1 minus alpha quantile for this F distribution with g minus 1 and n minus g degrees of freedom. The other thing I'll mention is that the theorem still holds for unequal group sizes. I've been working with little n, the size of all the groups, but that is not required for an ANOVA. And in particular, that is the jth group has n sub j observations. This capital N is just the sum of n sub 1 out to n sub g. So in R, we have this ANOVA, and we get what's called an ANOVA table. I will talk about it more on the next page, but just to go back to our earlier artificial data set, we see the table that is output. We see the degrees of freedom, the sum of squares, the mean square, the F observed, and then the probability. But let's talk about this table in more generality right now. So the ANOVA table, what we see here, this first row, treatment or between groups, we see listed degrees of freedom, sum of squares between, mean square between. We have our observed F statistic, and then our p-value of the ANOVA test. The second row, residuals, it's also known as within groups. We see its degrees of freedom, sum of squares within, and mean square within. You'll note that we have this total row, generally in an ANOVA table, where degrees of freedom add, so degrees of freedom between plus degrees of freedom within equals the total degrees of freedom. Sum of squares between plus sum of squares within equals the sum of squares total. Okay, I just want to summarize by moving toward what we're going to be getting into and later in this module. So in this lesson, we tested for equal means for more than two groups. Our null hypothesis is that, well, all G means are equal versus the alternative, at least two means are different. We separated the variation into two components, between group variation, within group variation. So after adjusting for the degrees of freedom, we arrive at the ANOVA F-test for the null hypothesis. Inside Canvas, you will practice the R function ANOVA in this lesson. Now, the group identifiers here are coded in one variable or one factor. That's the one-way part of one-way ANOVA in this lesson 1. But we will consider two factor variables in a two-way ANOVA later in this module. Thank you so much, class.